All right, so we are beginning our final segment, well, our next to final segment on this course. And now we're going out to the farthest scales, the biggest scales. We're talking about cosmology and the origin and evolution of structure in our universe. The last segment of the course will be on the existence of life in the universe, because it turns out it does have an intimate connection with the biggest scale context of our universe. We'll get to that on the last day of class, but we have probably both today, Monday, and then Wednesday will both be on just cosmology. So these are the things we're going to talk about. Let me get my little marker going here. We're going to talk about Olber's paradox, and then large-scale structure and its relation to dark matter, the discovery of the cosmic microwave background and what it means, and the evolution from there to dark energy, and yeah, an ET phone home. That's really, we're actually going to put that into a separate show. A separate show, by the way, which is already recorded, because I did it as well for my Astro 25 class, which just concluded. All right, so the first point is, let's take ourselves back to Newton's time and imagine a universe that would make sense in a natural context. Again, obeying maybe to the letter of the law almost, Occam's razor. Simplicity is usually truer. So now we imagine a universe that does not have an edge. It doesn't have an edge because if it had an edge, then you'd have to ask, well, what's beyond the edge? And that's an embarrassing question. And so maybe we should just get rid of the question and say, well, there is no edge. It just goes on forever. A universe of, in Newton's time, we didn't think in terms of galaxies. We thought in terms of individual stars. But the argument holds well either way, whether you think in terms of stars or galaxies. So if the universe goes on forever, then you can ask also, well, has the universe always been here? And if you postulate a beginning to the universe, then you have to ask, well, what happened before the beginning? And that's embarrassing. So let's get rid of that question and say, well, gee, you know, if you're going to postulate a God who's been here forever, then why can't you just postulate the universe itself, which we already know actually exists, as existing forever? So that's our base case that we're going to start with. A universe that has always existed. It's been infinite in space and time, no boundaries in either one. It turns out there's an extremely easy way to rule that out. And that is that if you look out in space, sooner or later, every line of sight is going to run into a star. And the reason for that is because the stars go on forever. That's our postulate. And just like these trees here, no matter how, no matter where you look, sooner or later you're going to run into a tree. So we got a forest and trees problem. Similarly for the stars, and since there's been infinite time for the light to get to you from the stars, then it has indeed gotten to you, and that means that the entire night sky should look as bright as the surface of a typical star, and we know how bright that is because our sun is a typical star, and is blindingly bright, and it's 6,000 degrees, and that means you are inside of a 6,000 degree oven, and of course that means you are going to be 6,000 degrees, and you'll be dead. So clearly that is not the situation. Newton himself realized this, but he couldn't seem to get the rest of the world to appreciate the real paradox there. And it waited for another couple of hundred years until Olbers, a famous observer in the 1800s, astronomer, pointed it out again, and this time the paradox of it all stuck. And so it came to be known as Olber's paradox. Why is the night sky black if the universe goes on forever? So what we've done basically is a little proof by contradiction. So either one or both of our starting assumptions must be wrong. Either the universe is not infinite in space, or it had a beginning. It's not infinite in time. One of those two must be the new case. All right, now it actually gets a little more complex because of the issue of redshift, but the basic idea actually remains. So could the universe be finite in time? Could the universe have had a beginning? Well, the Hubble Deep Field, this was a 3-day long exposure taken by the Hubble Space Telescope fairly early in its life. Took an incredibly long, I don't know, 40 hours, 50 hours, I forget. This is back in the mid-1990s, 25 years ago or so. It took the ultra deep field, and what we have circled here in green are galaxies that are incredibly far away. And you'll notice that each of these is a little teeny tiny red dot. I don't know if you can see that there's a redness there. These are distant galaxies. Even the more nearby galaxies, though, you can see, are not dominated by the usual spirals that we see in our local neighborhood. Spirals and barred spirals make up most of the bright galaxies in today's universe. Now remember, as you're looking out in space, you're looking back in time because the speed of light is finite. So if this galaxy here is 1 billion light years away, then you're seeing it not as it is today, but as it was 1 billion years ago. And I want you to realize that as you look out, you're seeing galaxies that are more and more typically irregular and colliding and elliptical, the products, as we saw, of galaxy collisions, or irregulars like this one here. And so basically galaxies look different as you go out. They don't look as relaxed. They look more early in their evolution, a more collisional and violent and unsteady state situation. So distant galaxies really do look different. We also know, as we already saw in the last chapter, that active galaxies are more common. Active galaxies being galaxies that put out most of their light in something other than starlight. They're dominated by X-rays and radio waves and ultraviolet and infrared and a little of everything. And a lot of that is from the black hole at the cores of the galaxies, and the black holes are active because there's still a lot of new infalling stuff that has low enough angular momentum to fall straight to the middle and power the accretion disks around those black holes. And quasars are more common distant in the distance. And in fact, not only they're more common, there are no quasars in today's universe. There are no quasars that are nearby. The nearest quasar is 3 billion light years away. That means 3 billion years ago. That's a quarter of the way back to the beginning of time. So clearly the universe is evolving. So that's our conclusion from these observations I'm summarizing now. We do not live in a static, steady state universe. Now I remember back when I was a kid, and I was first getting interested in astronomy in the early 1960s, and I was actually kind of a fan of the steady state universe. The idea that somehow, some way, the universe has always existed in pretty much the same way it looks now. Individual characters come and go, just like individual people come and go. But the humanity on Earth has been around for a very long time. Maybe the universe has been around infinitely. It was sort of philosophically satisfying, and also because I was pretty down on the idea of a godlike creation to the universe, religion in general. As you all know, I still am. However, the steady state universe turns out to be wrong. So, oh well. And we'll see how we disprove that. So the first notion to realize is something we already talked about before at the end of talking about the distance ladder, and that is the Hubble law, the Hubble expansion. So Hubble discovered in the 1920s, and of course the observations have been extended to much farther distances now, that the galaxies are moving away from us. All galaxies, virtually all galaxies, are moving away. Only a few nearby galaxies are moving towards us. And they are moving in such a way that if you look at galaxies twice as far away, they're moving away from us, as it turns out, twice as fast. And if they're 3 times farther away, they're moving 3 times as fast. And it's exactly the kind of expansion that you would get if you're thinking about raisins in a raisin cake. So there's a famous analogy that still holds as a great analogy today. good enough to actually show a picture. I'll do that in a moment. But think about the implications of that. So if the galaxies are moving away, then if we run the movie backwards, we're going to end up having a universe that is more crowded. And if you go back far enough, the galaxies are even on top of each other. Clearly that's got to be a time before the galaxies had even formed. And if you go back further still, the galaxies and even the stars would be on top of each other. And clearly that's got to be a time before the galaxies and the stars had even formed. And all you must have at that point is just the raw material out of which stars are formed, which is almost all hydrogen gas. A little bit of helium. So it suggests the idea that maybe the universe began in a hot, dense early phase, and perhaps even in a singularity, a Big Bang. Now the word Big Bang was coined by Fred Hoyle, and he actually wasn't a fan of the Big Bang idea at all, and he coined it as a term of derision, a term, a put down of the whole idea. But the name stuck, probably because it just rolls off the tongue so nicely, Big Bang. 2 B's, 2 syllables. I mean, what could be simpler? What could be easier to say? So it's stuck, and we use it now. We do not use it as a term of derision because the observational evidence to support it is now overwhelmingly large. But yeah, so there you go, raisin cake. So imagine the raisins, and the nearby raisins are going to recede from you. Okay, so that's us. Now, in this particular cake, there is one problem. There's a boundary to the cake. So what you really have to imagine to get this analogy right is forget the boundary. This is a cake. It is a big cake. I mean, it's a really big cake. It's a cake so big that there is no boundary on here. The boundary is so far away, it's meaningless to even talk about it, at least at this point. So it doesn't really matter what raisin you sit yourself on. Every raisin is going to see the other raisins moving away. So this raisin here is moving away, but slowly, because there isn't much yeast between us. But this one's moving away faster because there's more yeast. And if you go to raisins really far away, then they're moving away really fast. In fact, at a certain point, if you continue that, you might think, well, gee, Rick, that seems to imply that if you go far enough away, the galaxies are moving away from us faster than the speed of light. That makes no sense. The whole idea must be bogus. No, it's not. And we'll come back to that. But first of all, we want to look for observational consequences that go beyond just the Hubble flow expansion. So as you go back in time, the density goes up, and you go back far enough again. You have raw material, just gas, hydrogen gas. If you go back far enough, then that gas is dense enough that it is at 3,000 degrees. So just imagine gas in the piston of a car. So as you press that gas, and that gas mixture, gasoline in this case, mixture, then it'll get hot enough to eventually ignite with help from your spark plugs. And actually, you don't even need spark plugs if it's a diesel engine. And that tells you that temperature and density go together. If you press them in such a way that the heat cannot flow outwards, and the heat can't flow outwards here because there is no outwards, and we're talking about the whole universe. So the temperature just goes up, and there's a very simple relationship between the density and the temperature. We'll show you that in a second. But anyway, the temperature goes up as you go back, and you'll find that if you get to a time only 300,000 years after the supposed Big Bang, the moment when everything would be at the same place at the same time, the temperature of this gas is 3,000 degrees, and that's a very magic temperature. That's the temperature at which hydrogen goes from being an ionized gas to being a neutral gas. So as a neutral gas, we have a proton and an electron going around it. And we already know from chapter 5 that the only way that a neutral atom can interact with light is to have the electron move between bound, discrete, quantized orbitals. And the large majority of the photons of light that are moving around out there are not going to have the right wavelengths to do that. So a neutral gas is pretty much transparent. You can look right through it. Yeah, there's a few wavelengths where the light is blocked, absorbed, scattered, but the vast majority of the wavelengths you can see right through. But if you go back before that time, then the temperature of the universe is so hot that the hydrogen is an ionized gas, and you can't see through that. Okay, an ionized gas is opaque. So, drawing a picture of that, you would see a universe getting denser and denser, and the galaxies would until eventually be on top of each other, and then the stars would be on top of each other, and then you'd see a gas, but you wouldn't really see the gas because it's still transparent. And you go back and you go back and you're back before the time of stars and galaxies, and so there's nothing really to see, except it finally gets to a point where now it's 3,000 degrees, and as you run the movie backwards further, suddenly you can see. You can see the opaque surface of that hot gas. And so the prediction is that if there really was a Big Bang, you ought to be able to see 3,000 degree gas radiating at us from all directions. Now you might say, well, Rick, you just told us that, wait a minute, if we're surrounded by stars infinitely, they'd all be filling up every last square arcsecond of sky, and they would make us 6,000 degrees, like the surface of a star. So, okay, this is a little cooler, 3,000 degrees, but still, we'd be baked, we'd be cooked, we'd be dissolved, we'd be burnt to a crisp, we'd be ionized. We don't see that. Yeah, okay, good thinking. But there's one more ingredient you have to add in, and that is, remember, the Hubble expansion. So the farther away this stuff is, the faster it's moving away from us. And it turns out when you get to this point, only a third of 1 million years after the Big Bang, that stuff is moving away from you at 99.9% of the speed of light. And that means, as it turns out, that light will be redshifted then. And it turns out if you take a thermal spectrum of, just like starlight, take a thermal spectrum and then you redshift every single photon by the same amount, by the same fraction, same factor, if you will. It's going to be larger than 1, not really a fraction. It turns out if you redshift all of those photons, you will still have a thermal spectrum. And so you can still meaningfully apply a temperature to the radiation that you see. It doesn't literally mean that the gas is at that temperature exactly. It's really a spectrum of light from a distant time when it was actually much hotter. But we can apply a temperature to this. That's the interesting thing. It's just part of the way the laws of light work. Okay, so we should say a 3,000 degree sky, but redshifted by a factor of a little more than 1,000. And so it turns out to be a very simple thing to apply that same factor to this temperature of 3,000 and get what you should actually expect. And that is a temperature of about 2.7. Sorry, this looks like children's drawings, but it's our wonderful software here. 2.7 degrees Kelvin. That is very cold, okay? 2 degrees above absolute zero. And that kind of thermal spectrum does not radiate in the visible light like 3,000 degree red giants do. And it doesn't even radiate in the infrared. It radiates all the way out into the microwave. Uh-oh, I misspelled microwave. I'll fix it at some point. Microwaves, yeah. Maybe more memorable because it's misspelled. Anyway, microwaves. So that's what we should actually see. That's the real observational test. So photons were first able to travel freely with little chance of further absorptions beginning 300,000 years after the Big Bang. The universe was opaque until then, so you cannot see through that and see what the universe looked like earlier than this, not directly. But this cosmic microwave background in all directions should be observable. In fact, 99% of all the photons in the universe should be cosmic microwave background photons. So this graph just shows temperature as a function of time. This is a very compressed log scale 10 to the 15th seconds, that's about where we are today. That's how old the universe is, measured in seconds. You could go back all the way to 10 to the minus 33 seconds before you get to the quantum time, and then you could go back further than that if you want. And, well, maybe that's not right. Maybe 10 to the minus 45 is the time. 10 to the minus 33 seconds is different. Anyway, the temperature goes up. It goes up in a log-log scale linearly. And that's because it's an adiabatic expansion. Okay, so what should this opaque surface look like? So there you go, 99% of the speed of light, 99.9%. So it's Doppler shifted by a factor of 1300. It should look like 2.7 degree thermal light. It's in the microwaves. Now, Princeton physicists actually worked this out in the 1940s and actually started to look for it when we finally had the technology to build microwave detectors. And they realized that this radiation should be strong enough that you don't need a humongo massive telescope, just a little, bread box sized detector, but it's got to be pretty high tech, liquid helium to cool it, and lots of high tech stuff, but basically not a very big thing. And so they're putting this up on the roof of the physics building at Princeton. But before they had it finally working and calibrated and everything ready to rock and roll and take real data, somebody who knew these guys also knew another group who had nothing to do with astronomy, but they were part of the team that was building the first intercontinental telephone system using satellites. And the idea there is we beam microwaves from Earth up to satellites, and then that's re-beamed back down to, let's say, Europe. And so we can talk to Europe by using satellites, and of course all your cell phones work that way. And that's why there's always this annoying delay, and that's because you have to beam up to 22,000 miles above the Earth where the geosynchronous satellites orbit, and then it has to be beamed back down. So you're talking roughly 40,000 kilometers, taking into account sideways motion, maybe 30,000, but two ways, 60,000. 60,000 out of 300,000, you're talking about a third of a second. There's about a third of a second delay between the time you speak and the time people hear you. And even phone calls across town now have to go that way because that's the cheapest way to do it. At least if you have a phone. Nobody has a landline anymore. They're just too expensive. It's just outrageous. So we all have to put up with this delay. And I've noticed that nobody really seems to quite have that down yet. It's just a human genetic thing, I think. Anyway, we're getting off topic. So anyway, these Bell Labs people were noticing in their big antenna that they were talking to the satellites with, that they had this persistent noise. And it was a kind of a white noise, almost a white noise. It was a noise that didn't have any structure to it. And it was the same no matter where they aimed their antenna. And so very naturally they thought, well, it's our equipment. Maybe we got a hold of some bad diodes from that, North Korean distribution company or whatever. Okay, they were looking for noise in their equipment. And the great thing about these guys, Penzias and Wilson, is that they were really diligent. They were really good, scientifically minded engineers, and they didn't just say, "Oh well, I guess that's as good as it'll get, and let's forget about it." They really wanted to know what was wrong. So somebody who knew about Penzias and Wilson and also knew about the Princeton team, Dickey and Peebles, got these two guys together, and it turns out that these guys scooped the Princeton gang. And now one of the things that annoys me, mostly I agree with the Nobel Prize awarding committee, at least when it comes to the sciences, not economics, not at all in economics, but then it's not really an economics Nobel Prize. My Astro 7 students are hearing a lot about that lately. Anyway, mostly I really agree with the awards for the Nobel Physics, but not this time. Okay, Penzias and Wilson were deserving, but so was Peebles and Dickey, because they actually almost got there first, and they actually knew what they were looking for, and these guys, great as they were, they didn't know what they were looking for. Penzias and Wilson, Robert Wilson. Arno Penzias. Great characters too. Great people to interview. Okay, what'd they see? Well, they saw the microwave background. They just saw it in one or two frequencies though. So after that, we decided it was time to build a real microwave receiver that would do a better job, and eventually we got to the point of designing and launching COBE, the Cosmic Background Explorer. And I was actually getting my PhD at UCLA at the time that Ned Wright was there, and he was a central figure in the design of that instrument and the interpretation of the observations, and he was also on my PhD committee, so it was pretty cool. Ned's a great guy, if you ever get a chance to meet him. This is the first data that they got back from COBE. And so what you see here, this is an all-sky picture, okay? So you have to take a sphere, you have to cut it open, and then you have to flatten it out onto a plane, and it gets pretty distorted, so I have to interpret this. What you're seeing here is one side of the sky, it's extra hot, and the exact opposite side, 180 degrees away, it's a little colder. Now, they've color-coded this, and the colors make it look pretty extreme, but actually it's pretty tiny. It's extremely tiny, but not quite as tiny as they were expecting, or at least some people were expecting. Remember, this is back in the mid-1960s, and we had not yet seen the great data from Vera Rubin and her gang, and really confirming what this crazy Fritz Zwicky had first discovered, and that is dark matter. So dark matter was still controversial at that time. But what was noticed is that the simplest interpretation of this pattern is that we here on Earth are moving relative to the cosmic background, relative to the entire universe that is around us. We are moving relative to that. And we're moving in this direction so that these photons are a little bit redshifted, and we're moving away from this direction, and so these photons are a little bit blue shifted. Excuse me. These guys, okay, we're gotta remember how they decided to really color code this, because there's two ways to interpret red and blue. I think I'm interpreting it backwards. So let's say this side's red shifted, this side's blue shifted. Okay, it doesn't really matter which direction, because there's no stars here, so you don't really know. But there is one thing you should notice here, and that is these blobs. And these blobs are all along the flat line, and the flat line is oriented along the equator of the galaxy. And basically these little blobs are interstellar clouds along the galactic equator, the plane of the galaxy that we live in. They're cold too, after all. Star formation best happens when it's really cold. 30 degrees Kelvin still has a pretty significant emission at 3 degrees Kelvin. So these are just interstellar clouds. These are cold interstellar giant molecular clouds. If you really want to understand the cosmic background, you're going to have to clean your data of that signal. So yeah, these are foreground microwaves from interstellar clouds. In order to properly measure, you have to get rid of that. Very tricky job. So I remember having interesting conversations with Ned Wright about that and how hard it was to really do that well. And we have done it well, and we have been able to clean the data very well. And now here it is as a drawing, and now we're seeing directions. So this is showing that we are heading towards this direction. The hot spot, the place where the cosmic background is brightest, but only by a tiny amount, 1 part in 100,000, is not a 1 part in 100,000, 1 part in 1,000. Anyway, it works out to 660 kilometers per second. Compared to 300,000, that's not much. Okay, so 0.02% or something like that. It's always easier to remember as just a velocity. So we are moving in this direction relative to the entire observable universe by about 660 kilometers per second. It turns out there's a very easy explanation for that. Where is the nearest rich cluster of galaxies? It's the Virgo cluster. Look, there's Virgo. Where's the Virgo cluster? It's right there. What's the next big and even a richer and denser cluster, the one that Fritz Zwicky used to find the dark matter? It's the Coma cluster. Where's the Coma cluster? Oh, well, it's right here. And then what's the next big thing? Well, the next one took a little bit of sleuthing to do. Actually, Sandy Faber up at UCSC was central in that investigation. And that came to be called the Great Attractor. And it is a large concentration, another giant galaxy cluster, but it's not so easy to see because it's behind the dust in the Milky Way. So it was really only found with a lot of extra work. But that's down here in Centaurus. And if you add all these up and throw in the Leo cluster, and the Leo group is up here as well, and the Ursa Major cluster, and kind of average together all the lumps that are going to be pulling on us, there's really a strong excess in this direction. On the opposite side of the sky, there really isn't much. So we just happen to live in an area where there's a giant super clusters of galaxies, and they're all on one side of us. They're all in this direction. And so we've been yanked by gravity to this direction. And we've been yanked up, slowly accelerated, foot on the accelerator, for 13 billion years, enough to pull us up to a velocity of 660 kilometers per second, in excess of what you'd expect in just a motionless local universe. Now, the interesting thing about that number is way too big to account for by the visible stars in the galaxies that define all of these clusters. What I'm telling you is that velocity is so big because it's telling us even dark matter is lumpy on scales this big. Now we're going to begin to see that again when we look at the cosmic background again. But anyway, here's independent evidence just looking at galaxies themselves from the Great Attractor that dark matter dominates on even bigger scales than individual galaxies or individual galaxy clusters. So I use the term the observable universe. So what the heck's the observable universe? We have to make a distinction between the universe and the observable universe. If there is something that is moving faster than the speed of light away from you, there's no hope for you to see it. The light can't get to you. So the observable universe is that part of the universe that is moving away from us by the Hubble expansion. But it is moving away from us slower than the speed of light, and therefore the light has had a chance to get to us since the beginning. So there is an edge to the observable universe, but that is an edge or a horizon, probably a better way to use the word. But it's an edge not in space, but an edge in time. And every different galaxy has their own observable universe. So we don't all share the same observable universe because we're all in different places. Think of it as a sphere that surrounds us. And that sphere is going in a direction that is expanding, and it turns out actually enclosing more and more matter as we go on. That's a whole separate story. We won't come to that till later. Maybe not till our next class. Okay, so here's another way to think about it. Here's my little thought experiment. Now forget about the fact there's no air in space, and so like the tagline in the movie Alien, in space nobody can hear you scream. We're going to imagine that in space people can hear you scream, or in this case can hear firecrackers go off. So we're going to construct this moment. Let's imagine the entire universe is filled with firecrackers. Now we don't need a firecracker every square millimeter, just a firecracker every, whatever you want. Whatever density you want. But the thing is, we're going to set them all off at the same moment in cosmic time. So we're going to set them all off at once. What are you going to hear? Are you going to hear one ginormous ear-splitting bang? Or will you hear a continuous roar? Well, anybody who's been in Yosemite Valley during a thunderstorm, is kind of the most dramatic place I can think of it, knows that what you would hear is a continuous roar. So there is one instant when the lightning goes off, but as that lightning, as that crack of sound reverberates off of different mountains and different valley walls, it takes different pathways to get to you, and it eventually, it could take 10, 20 seconds before the last bit gets to you because sound travels rather slowly. So you'd hear a continuous roar, and it would never end. There's always going to be some place that is experiencing the Big Bang right now. So when we look out at the cosmic background radiation, we're looking back in time to 300,000 years after the Big Bang, and we're seeing the first emergence of the light that was part of the energy of the Big Bang itself. So again, you may say, well, gee, that sounds like stuff going away from us. There is stuff going away faster than the speed of light, but you said that was the ultimate speed limit. Yeah, so now this may sound like a kind of a lawyerly beg off on the ultimate speed limit law as first discovered by Einstein, but it's actually not. I know it sounds kind of weaselly, but it's actually perfectly true, and that is that space itself does not have that speed limit. It's only matter moving apart from matter in that space that has that speed limit. So space itself should be thought of as what is moving, and it's carrying the galaxies with it. So space is expanding. And so what's really a better way to think about this cosmic redshift is not so much that the galaxies are moving away from us, although they are, but what's better to think about is that space is expanding. And the photons are tied to the space. And just like a rubber band tied to an invisible medium, if it's a sticky medium and the rubber band is stuck to it, as the space expands, the rubber band is going to get stretched. And think of the little waves of light on that, in that medium, in that space, they're going to get stretched too. And they get stretched and their wavelength gets longer. And so what we're really seeing is a cosmological redshift, but it's kind of indistinguishable from a Doppler shift. And we already did the Doppler effect, so I thought I'd try and appeal to your intuition and in that way first, but then this way is probably a little more accurate. Space is expanding, stretching the photons with it. All right, so the discovery of the cosmic background showed that the Big Bang really did, well, we can get within 1/10 of 1% of the way back to the beginning and see observational confirmation of this expansion. So what we think is that the universe really did begin in a Big Bang. But do we have better evidence that can go back even further? And yeah, we do. We can go back to a time only 1 to 3 minutes after the Big Bang. And then the temperature is only, well, I mean only, it's like much hotter. It's millions of degrees, and that's hot enough for nuclear fusion. So you'd have expected that some of the hydrogen would be cooked into helium. Now, by the time there was enough helium around, the density was already too low, though, for helium to fuse. Remember what stars needed to do in order to fuse helium into carbon. They needed both a very, very hot temperature, 10 times hotter than hydrogen fusion. They needed temperatures of 180 billion degrees. 180 million degrees. But they also needed extremely high density to get those helium collisions to happen frequently enough that you could get 3 of them to combine before the 2 that combined fell apart. And 3 heliums is a carbon. And so when you do the actual calculations using Monte Carlo simulations and the interaction rates that you'd expect from the nuclear cross-sections, you find out that the universe itself should not have cooked any carbon or oxygen or really anything else. A little tiny bit of lithium-9, 1 part per 10 billion of lithium-7 and beryllium-9. But basically, all you get out of the Big Bang is hydrogen and helium. So we can test that. We can look at the abundances of the elements in the oldest stars, the stars that formed right after the Big Bang. Well, we know where to find those stars. They're right here in our own galaxy. The globular clusters in our own galaxy, we've age dated them, thanks to the HR diagram, to be 12 to 13 billion years old. They were born roughly a billion years or even less after the Big Bang. And what are those stars? Well, we already told you what they are. They're POP2 stars. You should remember that. Hint, hint. Okay? You should remember that. Globular clusters are dominated by population 2 stars that have only hydrogen and helium. They are the oldest stars in our galaxy. Just in case somebody asks you on a quiz or something, okay? Okay, so the test is successful. Indeed, the earliest stars are made out of the stuff that came out of the Big Bang, according to very well verified, very confident nuclear physics calculations. So you can do those calculations, and you can actually go to one step further and ask, well, what was the density of the universe at the time that that happened to create the amount of helium? And there's another species that's very sensitive to all this, and that is deuterium. So 2 protons will smash together and form a helium-2, which will immediately turn into deuterium, or heavy hydrogen, by a weak force decay. And so both of these are sensitive detectors of the actual density of the universe. And it turns out the actual density of the universe best fits the data right about there, at about 0.04. 0.04 of what we call the closure density, so I'm going to get to that in a minute. But so now we're going a little bit beyond, and we're saying, well, not only does it look like we had a Big Bang origin, but we know the density of matter in the Big Bang. And it's showing that the density of ordinary matter, all the matter you think of when you think of matter, not talking about the dark matter, talking about ordinary matter, all the 92 chemical elements, is only 4% of the matter and energy of the universe, if the universe has the closure density. So I haven't told you what that means yet, but I'll tell you right now that physicists have always had a strong confidence, or be willing to bet that the universe really is at so-called closure density, because we know how to make a universe that has closure density. We don't know how to make a universe that is far from closure density, which would be required if that's all the matter there really is. Okay, so how did structure emerge from this uniform so-called primordial soup? So the current universe is lumpy. It's very lumpy. Stars are about as soupy as water, and they're spaced away from each other by, even within a galaxy, which is a relatively dense place, they're 1 million diameters apart from each other. Galaxies are less dense. They're spaced, though, still maybe 20 or 30 or 50 diameters apart, depends on the environment. Less than that if they're in a rich cluster, but still, there's a fair amount of empty space. Galaxies are pretty lumpy, pretty easy to identify. Even galaxy clusters, the rich ones like Virgo and Coma, pretty easy to identify. They're lumpy. They're not nearly as lumpy as galaxies, and galaxies aren't nearly as lumpy as stars. But then that's also telling you something, right? That was how we decided that the dark matter must be cold dark matter. That was what we arrived at the end of our last lecture. So the initial density fluctuations, though, is now what we're wondering. So, you think of a hot gas, it's extremely uniform. So far, we haven't come up with any reason here why the universe should be lumpy at all. I mean, if the universe is flying apart at speeds that are comparable to the speed of light, why did anything at all form? Why didn't the individual atoms just fly apart and no structure at all? So that's our next set of observational clues. We want to know, how can the structure of the universe tell us what is the nature of the matter that is really being the gravity that is pulling stuff together and letting us see what we see. And so now we get to what we call topology, the geometric form of the matter concentrations in the universe. There's lots of possibilities. It could have been a meatball topology. That would be one where the density is concentrated into spherical or roughly spherical lumps, surrounded by empty space on all sides, and then another lump somewhere else. That's not the only possibility. That may be the easiest one to come to mind, but that's not the only other possibility. You could have the opposite of that. The Swiss cheese analogy, where the roundish things were actually the vacuums, and then the matter was where the cheese was. So then that would look a lot more complicated to try and draw. And then something that's sort of in between, a filamentary structure. So what does the universe really look like? Well, galaxies are tracers of the matter. They're tracers even of the dark matter. We already saw how the dark matter was concentrated around galaxies, that the density of dark matter is revealed by Vera Rubin's data, and all data since, that falls off as roughly 1 over r squared. The dark matter is densest right where the ordinary matter is, in the central bulge of our galaxy, and it's true for other galaxies as well. Okay, but the dark matter is not as concentrated as the light matter. But still, the light matter, the stars here, are like beacons shining within larger scale structures that tell us where the major matter that dominates the universe, the dark matter, actually is. So what do we see here? Well, we see what's called the Great Wall. This is towards the northern cap of the visible sky and looking towards our Milky Way. So that's the Great Wall. And there's the Great Wall of the South. And then there's kind of another wall there, and there's a bit of a wall there, and there's some filaments there. There's definitely filaments, but now I don't want you to get confused with another direction. Here's another filament. And that is this direction. Now, that's us, okay? We're there. And this direction here, why don't we see any galaxies here? That's probably the first thing you're wondering. Well, they deliberately took those out. This is actually an old classic survey, a really important survey that first gave us great cosmological clues, done by Harvard University, Geller and Huckra were the initiators of the study. And this region here is so close to the plane of our own Milky Way galaxy, this angle here, that they said, you know, trying to judge brightnesses of galaxies and making sure we get them all is too hard. There's too much dust. It's too lumpy. It's too hard. You know what? We've got enough statistics. We're just going to throw this data away. So all the galaxies that were in here, we just threw them away, counting on that all these galaxies in these other directions, like cones, like those funny cones, you know, that dogs wear. This is sort of like what you're doing. You're looking sideways out of a cone. Think of a circular edge to the cone. It's up here and down here. And now we're going to project that cone onto the sky, and we're going to just take a slice out of it. So this is, in fact, the name's often given to the papers published here, a slice of the universe. And we're looking at the galaxies in that slice. And you can begin to see filaments. That's the point. Filaments. The universe is filamentary. Now, here's a deeper survey using infrared to help us, and going out much further. And now the filaments are more obvious. Actually, you know what? I want to go back for a moment. These vertical things here that are aiming right towards us, I never finished that thought, did I? This is the so-called fingers of God effect. God is pointing his evil hand, his fingers at us. You are sinful and evil, or whatever he's saying. Actually, these are not fingers of God. It's just a colorful language. What these are is the Doppler effect of the motion of galaxies inside dense, rich clusters. That's the Virgo cluster I just circled. And look at it, some of it actually goes beyond us. If you just literally interpret the velocity, throw it into the Hubble formula, and infer what the distance is, you're going to get the wrong answer. Because there's a lot of that velocity that's not due to the expansion of the universe. It's instead due to the motion of clusters inside of galaxies, galaxy clusters. So you have to be careful. You have to be really careful. And if you're really careful, then you can find that these clusters actually have velocity. And this velocity is internal, and it shows itself as the fingers of God. So it's one reason why the Hubble formula is not super accurate when it comes to trying to get distances, especially nearby. Anyway, when you have a big survey like this, then the fingers of God effect is smaller, and it's a little more reliable as a distance indicator, at least if you're not worried about small-scale motions. The point is that the galaxies are knots within dark matter. The dark matter is arranged in a filamentary way. And in fact, that's exactly what we would expect. We would expect that the lumps in the universe created by dark matter, we'll come to a reason why later, but imagine that those lumps are just like amorphous lumps, kind of like elliptical galaxies. We talked about how they're triaxial. They're random collisions and random impact directions, and so you'd expect that all three dimensions would be different. Now imagine that in a context of an expansion. So what you would have is one particular direction would be, doesn't have to be along an X, Y, or Z direction, it can be any direction, but there would be some direction along which the galaxies would experience the maximum density contrast. They would be sort of lumpiest. You know, there'd be a real sharp direction. Okay, there's a lot of stuff here, and there's not so much stuff going away from it. And that's the direction from which the galaxies would get the clearest command from gravity to collapse along this direction. So you'd expect stuff to collapse into pancakes first. So take an amorphous lump. It's got three unequal dimensions to it. It's defined its principal axes along its directions, where the matter seems to be oriented. And along one dimension is going to be the flattest, and that dimension is going to be the dimension that it collapses the first. So what we say is that lumps in the universe collapse along to make pancakes, and then the pancakes collapse to make filaments, and then the filaments drain to the middle and make lumps, zero-dimensional things. So things go from being sort of three-dimensional to being sort of two-dimensional to being sort of one-dimensional, filaments, to being zero-dimensional, galaxy clusters. Now, the speed with which that happens is going to be faster for the lumpiest things and slower for bigger things that are less lumpy. And so what you'd expect that when you just take a snapshot of the universe at this moment in time, like we're doing now, 13.72 billion years after the beginning, that you're going to see lumps that are in all three phases of that evolution. And that's exactly what we see. So we see a mixture of filaments, sheets, and lumps. And that characterizes the large-scale topology of the universe. And that's exactly what you'd expect if the universe was dominated by cold, dark matter. All right, it's now 10:30. It's time for me to say goodbye. I'm going to end our meeting right now because it's time for you to start your quiz. Your quiz is